Hello everyone. What we're talking about in these lectures is the first of the organ systems that are found in animals, which is the nervous system. So we're talking about that system that is in charge of detecting information, whether it's coming from outside or inside the body, and integrate that information and come out with some sort of response. So these are the topics that we'll be touching in this lecture. I'll divide it into two parts. I'll stop here until the summation part here, and then we'll finish up in the second part talking about evolution and the human nervous system later on. The topic we will touch now are the nervous system. So we'll review the nervous system and the nervous circuits, neural circuits. Then we'll talk about how is the signal generated. So we'll talk about membrane potential, the graded and the action potential. Then we'll talk about the receptors, which is where basically the neural circuits start. Then we'll talk about how the signal is propagated through axons. We'll talk about its transfer in synapses, and then how different graded potential, different stimuli in the neurons are basically added together or cancel with each other through the process of summation. And finally, we'll talk about a little bit about the evolution of the nervous system, and we'll finish reviewing the human nervous system. So the function, as I mentioned before, of the nervous system is to receive or to sense all the information from the internal and external environment. For example, light stimulation, it's a sort of information received, or sound and so on. Integrate that information and then formulate a specific response. This is done through transmission of the messages along these basic cells, which are the neurons, and this transmission also affects not only the overall body but also effector organs as well. Now, let's review the nervous system. We already talked about that when we were talking about the different tissues in the animal bodies. So it's made by three main type of cells. So you have neurons, some dedicated receptors, some of them are actually neurons, and glial cells. So when we talk about glial cells, we're talking about different cell types. We have microglia with a subtype called astrocytes, which have the function ultimately to support the activity of neurons by removing, for example, removing neurotransmitter at the synapses, or providing ions and so on. They have the function also to protect the overall nervous tissue from foreign invaders, such as viruses and bacteria and so on. And then you have a second set of cells, which are the oligodendrocytes and the Schwann cells, which are involved in making basically the signal, or the transmission of the signal through the axon much more efficient through the formation of myelin sheath. We'll talk about that in the second in this light here. So what oligodendrocytes and Schwann cells do is exactly the same thing. They wrap basically the axons of some type of neurons, not all neurons. These are usually those neurons that have very long axons. The axon can go up to meters long and can be very thin, so they can be combined together into nerves. And so these long and thin axons will be very inefficient at transferring signal. And so by adding this myelin sheath through either oligodendrocytes or Schwann cells, the transmission becomes much more efficient. We'll talk about that. And this transmission is referred to as saltatory, not salutatory, saltatory axon potential. Please remove this U from here. Now, the only difference between oligodendrocytes and Schwann cells is that they do this in two different locations. So the oligodendrocytes are those supportive cells forming the myelin sheath within the central nervous system, so in your brain or your spinal cord, whereas the Schwann cells, they do that in the peripheral nervous system, so the remaining part of the nervous system outside of your brain and spinal cord, so it will be in the nerves and so on. Now, the neurons are those cells that do transfer the signal. They can transfer a long distance, and then they integrate the signal. They are basically the big actors here in the nervous systems. Now, There are different type of neurons, we'll see, that can be classified based on function, based overall structure. Overall, you can identify common structure, at least in most of them. Some of them have the structure more or less enhanced. But there are three main structures that make up a neuron. The first one is the dendrites. The dendrites are these extension here, some sort of web-like type of or tree-like type of extensions here, which is where the information is received. This is where, for example, another neuron could form contact here through a synapses and transfer the information to this neuron through these dendrites. Now, all of them will carry that information to the second part of the neuron, which is the cell body. Here, all of this information ultimately get integrated at the very end of the cell body here, which is the hillock area here, which is where all of the stimulation gets basically integrated and basically can be converted eventually into an action potential, which will go through the third structure here, which is the axon. The axon is that structure that carries away the signal now from the body to either the effector, which could be, for example, a skeletal muscle or another neuron. Now, neurons can be classified in different ways. Can be classified based on morphology, so the way they look, and in this case they are classified as unipolar. In this case, as you can see, there is basically no dendrites here, so the stimulation would take place at the cell body and eventually would generate a signal going through the axon. Then you have bipolar type of neurons. Sensory neurons are oftentimes bipolar, and so they have the dendrites will be actually on this side here, could be encapsulated or not, or could be free, and that's basically detect sensation here. It brings it to the body here, and then here they would have the axon. Now you can have pseudo unipolar neurons similar to the bipolar one, but now you have that the actual body comes out from the overall axis made by the dendrites here and the axon here. And finally, you might have multipolar type of neurons, such as the Purkinje neurons, for example, that have a big web of dendrites here, clearly characterized, and they're all connected to the body here. And so now, based on function, instead, neurons, no matter the way they look, whether they're bipolar and so on, or pseudo-bipolar and so on, they can be classified into three different groups. You have afferent neurons. Afferent neurons are also referred to as sensory neurons, and are those that basically are in charge to bring the sensory information to the central nervous system, so ultimately to interneurons. Interneurons are those neurons in between, which are involved in the integration of the information. So they will get the signal from afferent neurons, and basically they would integrate it, we'll see later on, through the process of summation, giving origin or not to a specific response. And then you have finally the third type, which are efferent neurons or motor neurons, which are the one that then will be activated after the information can be integrated, has been integrated, and they will bring ultimately the signal to some sort of effector. Could be a cell, or could be a muscle, for example, could be a gland, could be a different type of effector there. So afferent neurons, they basically bring the information to the nervous system, central nervous system. The interneurons will be within the central nervous system, whether it's the spinal cord or the brain, and the efferent neuron would take it out away from the nervous system, the central nervous system. Now, these are the three different types of functional type of neurons that you can find. You have motor neurons. These are efferent type of neurons. So that will be taking the information through several dendrites, integrating here at the axon hillock here, or spike initiation zone. Basically, it's the same thing. Information will get integrated here, and it would eventually generate a signal taken away from the axon and transfer ultimately to an effector, the final target of that signal. You may have sensory neurons. There are different type of sensory neurons. You'll see that. In this case, they will be actually detecting the information through the dendrites, whether directly or through other cells, and then they will take this information to some interneurons here, so not to an effector. And then you have Purkinje cells. These are Purkinje cells that are actually found in the cerebellum, and there will be some sort of interneurons where they integrate some sort of information, and they will connect with other neurons, trying basically creating more complex structures where very high level of integration of information can take place, which then could be transferred ultimately to motor neurons. Now, all of these neurons, they organize together in what we call basic neuron circuits. Now, neuron circuits can be very complex, okay, or actually even very simple. A basic neuron system, all it consists of, and we'll see an example later on, it's an afferent neuron, one interneuron, and one efferent neuron. So in other cases, you may have much more complex system. But all of them, ultimately, what they do, they detect some sort of stimulus, some information, whether it's light, pressure, pain, heat. These, through an afferent sensory neurons, will bring it to interneurons. Here you may have many of them. Imagine your brain. All of this information get integrated, and then through efferent neurons will be brought to the effector, causing the desired actions. And all these combine into networks, all these neuron circuits that basically connect what is called the peripheral and the central nervous system. We'll talk about that when we'll talk about the human nervous system as an example. This is an example of a very simple nervous system. It's the one that in some way is involved also in your walking or part of your walking. Obviously, walking is a very complex action. Okay, it can be controlled by your brain, and it's controlled. If I want to get up from my chair right now, it's my brain, right? I decide I want to get up, and I would activate walking. However, when you're doing it routinely, like you're going for a walk on the street, you're not, if you think, you're not always thinking about, oh, now I should move my right leg and then my left leg, so I should contract this muscle, then relax the other one, and so on. Your body is actually doing it. Your legs are actually somehow walking independently from your will. They're doing it. And they're sensing things and responding to that without you knowing. And they're doing that through very overall simple spinal reflex circuits. How do they work? Well, first of all, we have to talk about movement. Movement is caused by contraction and relaxation of skeletal muscles, which are those muscles connected to your skeleton. That's why they're called skeletal muscles. They're voluntary muscles. And movement in general is always caused by the antagonistic action of a pair of muscles. Think about your arm. Now, if you're bringing your head towards your shoulder, this action is actually caused by the contraction of your biceps and the relaxation of your triceps opposite to them. So you have two muscles there. You have the biceps and the triceps. They are antagonistic with each other. So what it means by antagonistic, when one muscle contracts, the other one relaxes, and vice versa. By doing that, you can cause the movement of the two bones in your arm, or more than two bones, but compared to each other. Okay, that's the activity of these two antagonistic muscles that allows the flexing of your arm. Similar in your legs, you have the quadriceps on the top, right here. This will be your quadriceps, and on the bottom you have what is called the semitendinous muscle. There are actually several of them. So they actually work in pairs. So one of them is referred to as the extensor. So they're both antagonistic. So they're antagonistic muscles here, antagonistic pair. And we could refer to one of them as an extensor. And the reason why the quadricep here can be referred to as an extensor is because when it contracts, it actually will cause the extension of your leg. So the knee here will move so that basically this part of your leg and this part will become aligned. Whereas the other one, the semitendinous muscle here can be referred to as a flexor, and the reason is that when it contracts, it actually causes the bending of your knee, the flexing of your legs, basically. So how does it work? Well, this can be controlled through your brain and so on. But when you're walking, they actually have different mechanisms involved. Now, one of them is the one based on the perception of ultimately pressure and stretching by this little organ that is present in your tendon here. It's called the Golgi tendon organ. This is basically a tiny little organ within the tendon that basically detects stretching and relaxation of the tendon. But detects particularly stretching which obviously will be a consequence of the contraction of the muscle. So this tendon here is connecting this muscle to your knee. Now, what you have is that when this muscle here, so when this extensor, the quadricep muscle, contracts, this tendon gets stretched, and here the tendon organ here, the Golgi tendon organ, will detect that. When it detects that, it's sending this message through this afferent neuron to the spinal cord. And what happens there? So this neuron gets activated in this neural circuit. And what it does there, it actually activates two interneurons. One of them, once it gets activated, actually it inhibits the motor neuron, so the efferent neuron at this point. That's the neuron that starts from your spinal cord here, and gets into the muscle and will cause it to contract. But now the activation of this interneuron here by this afferent neuron, caused again by the stretching of the tendon here, causes the inhibition of this motor neuron, and therefore this muscle which was contracted before will start relaxing. The opposite happens instead with the second interneuron that is actually activated by this afferent neuron. What it does, the activation of this interneuron actually now turns on, activates this second motor neuron, which is the one that activates the antagonistic muscle to the quadricep, which is the semitendinous or the flexor muscle here. By doing that, now you have that the relaxation of this muscle at this point will be paired with the contraction of this muscle. So the stretching, imagine you're walking, all right? You have extended your legs, so this muscle was stretched. Now this is giving the signal here through the spine. This signal is not going through your brain, and automatically causes this reflex of relaxation of the same muscle that had extended the leg, and the stretch, the contraction of the muscle that will cause it to bend. So you have stretched it, and now your leg will start bending. Will start bending until now you have the tendon here, which will do the same thing. You have a tendon on this muscle too, which works the same way. So once it gets this muscle contracts enough, so you have had enough at this point flexing of the knee, right? This starts sending the signal here and do the opposite. At this point would turn on this motor neuron and therefore the contraction again of the extensor, and now it will cause instead the opposite on the flexor, will cause it to relax. So this is just to give you an example of a very simple neuronal circuit here, which is referred to as one of the many spinal reflex circuits, which is involved in your case on alternating the contraction and relaxation of these two antagonistic muscles, creating the movement of your leg without you having to integrate too much information. This is basically activated directly. So it's just an example, very simple one. You have an afferent neuron, interneuron, efferent neuron causing their response. So let's move now to the next topic. So how is this signal that we just mentioned here? So you have, for example, the stretching now of the tendon that caused this signal. How does it work? How is it transferred through neurons? So in order to talk about that, we have to talk first of all about resting membrane potential. Now, if you take any cell, they would have some sort of resting membrane potential, and you can actually measure it by introducing an electrode, tiny little electrode inside the plasma membrane. It's called patch clamping. You can actually put it inside and measure the actual voltage that there is across the two sides of the membrane. So if you take a neuron the difference in voltage will be about minus 70 millivolts. This is measured by comparing the inside of the membrane to the outside, and therefore this negative value tells us that there is negative charge inside and positive outside. So this membrane potential is caused by the uneven distribution of electrical charges on the two sides. So in this case, you have lots of positive ions on the outside, negative ions on the inside, and therefore a difference in electrical potential between the two sides, which is correspond to the resting membrane potential. Now, what contributes to that? There are different things. So let's focus on neurons. So neurons have this membrane potential. By the way, it's the same potential that we're talking about when we're talking about cellular respiration, if you remember. When we're talking about the protomotive force in the inner membrane of the mitochondria, or when we're talking about photosynthesis, we're talking about the thylakoid membranes that had similar protomotive force. We're talking about ultimately a potential across the two sides of the membrane. So focusing on neurons here, as we said before, the difference here in membrane potential is 70 millivolts. So minus 70 millivolts because the inside is more negative than the outside. What contributes to that is the uneven distribution of protons, of sodium and potassium ions here. So what we have is that there is an active transporter. We talked about that in BIO358. It was an example of a primary active transporter that what it does, it transfers 3 sodium ions from the inside of the neuron to the outside against their concentration gradient, and it does the opposite for 2 potassium ions, transferring them from the outside to the inside against their concentration gradient. So this basically causes the concentration gradient of sodium, with sodium being much more concentrated on the outside than the inside, so about 10 times difference. The opposite for potassium, which is more concentrated towards the inside compared to the outside, about 30 times more. Not only that, but now what you have here is that inside you have also a lot of molecules, particularly proteins that are negatively charged, which still contributes to the negative environment on this side of the membrane. So when you put all together this, there is a difference in concentration of the two ions, positive and negative ions on the two sides, and therefore these membrane potential there, resting potential, that's how it's referred to. Okay, so now all of these can be perturbed or changed by moving these ions. For example, you can open a sodium channel here, and this will cause the influx of sodium ions from the area of high concentration to the one of low concentration. So from the outside to the inside. Obviously, when you do this, this will reduce the negative charge on the inside. Vice versa, if you open a potassium channel, you would have the opposite effect. So now potassium will go out following the concentration gradient, and therefore the outside will become more positive, even more positive than the inside. So this is the base of what we call the polarization or depolarization of the cell membrane. So now you have this resting potential of minus 70 millivolt in the membrane of our neuron. So now what would happen, again, for example, if you open a sodium channel here, and this happens all the time at the synapses, okay, you have the sodium ions entering inside, so they reduce the negative charge on the inside. What it means is that now the membrane potential, since it's measured from the inside to the outside, the difference here, it will become less negative, so we'll go more towards a neutral value here. This will cause a spike like this, which is referred to as depolarization of the membrane. The opposite you would have is if you open a potassium channel. Now you have potassium be more concentrated on the inside, it will go out. So you have that positive charge are transferring from the inside to the outside, meaning that this difference becomes even bigger, the difference between negative and positive ions. And therefore, the membrane potential will go from the resting value to a lower one. This is referred to as hyperpolarization. This is a typical of inhibitory mechanisms in synapses, whereas this is typical of stimulatory synapses. Now, hyperpolarization can be achieved by letting potassium ions go from the inside to the outside, opening one of these channels, or the opposite. You see some neurotransmitters, they actually act by opening chloride channels. Chloride is more concentrated on the outside. When you open a channel of chloride, it's not here, don't worry, I'm not showing anything, but I'm just pointing to something. So if you have more chloride ion here on the outside, they will go inside, therefore increasing the negative charge on the inside, still causing hyperpolarization, which again normally translates into an inhibition. Okay, so now you know what is the resting membrane potential and what is causing this uneven distribution of potassium, sodium, and other negatively charged molecules. Now, this potential can be changed, as you can see, either through depolarization, causing depolarization, or hyperpolarization by playing, basically by moving some of these ions around. Now, when this changes, you have a change in potential that can be of different types. Now, small changes in potential. So these are small changes that do not reach a certain value. Okay, in neurons, so changes that go from -70 here up to 50 will not be enough to cause what is called an action potential, the activation of an action potential, but will be causing what we call a graded potential. So this is a transitory type of change. Okay, it could be either depolarization or hyperpolarization, going back here. So it could be either go this way or this way, and it will be transient. So it would take place, it will spread in both directions, and when it's spread in that direction, the change will be smaller and smaller proportional to that distance. It could diffuse a few millimeters, but it will get smaller and smaller with the distance. All right, and it's transient. So basically, the membrane will get depolarized or hyperpolarized through a graded potential, and then very quickly we'll go back to its resting potential. So we'll go in a situation, again, spending a lot of time here, but it's good that you understand it quickly. So if you have depolarization, is not big enough. To be big enough, has to reach this threshold value of -50 millivolts. If it's not that big, it will cause this uneven distribution, temporary uneven distribution of ions, causing depolarization or hyperpolarization, but then the sodium-potassium pump here will quickly re-establish the resting membrane potential. Okay, so graded potentials, which are generated, by the way, all the time as synapses, okay, or by stimulation, compression of one of your fingers causing graded potential, which may or may not turn or cause the formation of action potentials through summation. We'll talk about that. But per se, every single graded potential is not big enough to cause an action potential, and that is just transitory. Okay, could be it will go in both directions, but then it will fade very, very quickly. Okay, this is different from action potentials. Action potentials ultimately are caused by graded potentials that, by summing up, they reach a certain threshold. If say you have two of them, they sum up and reach a change of 20 millivolts, so they go from -70 to -50, they reach, depolarization reaches this threshold value. At this point, this graded potential will convert into an action potential. Differently from a graded potential, action potentials, first of all, they're very long, so they can go a very, very big distance in the axon. They're generated here at the axon hillock here, and they go very, very far away. They can go a meter away, and they're sustained, so they keep going. They don't fade very quickly, and they're unidirectional. They go only in one direction, not the opposite way. We'll talk about that later on, why they are unidirectional. And so how does it happen? Well, they happen, as I mentioned before, when you have some graded potential that reaches this threshold value. Now, these causes, and we'll see better, because it's in the written form, but we'll see in the picture in the next slide. This causes ultimately the coordinated opening of two type of voltage gated channels, sodium and potassium channels. They open at different times. So first you have the voltage gated channels that open up. So once the graded potential reaches this value, you would have the sodium voltage gated channel that opens up, and this causes an influx of sodium from the outside to the inside, causing a big depolarization. Right? After that, then you have the potassium voltage gated. So the sodium voltage gated channel here will close at a certain point, and the potassium voltage gated channel will open up, causing the repolarization of the membrane going down. And this is what an actual potential looks like in terms of changes in membrane potential over time. Now let's see in more detail how it works. So as we say before, there are two important channels that are involved in the formation of the action potential. One is the sodium voltage gated channel. The other one is the potassium voltage gated channel. Voltage gated means that they get open up or closed by certain values of membrane potential. The sodium voltage gated channel gets open once the voltage of the membrane is higher than minus 50 millivolts up to a certain point, and you see it up to 30 pretty much millivolts right here. So how does it work? Well, there are two components to the sodium voltage gated channel. I can say sodium channel at this point, you know, is activated by voltage. There is what we call an activation gate. This is the one that opens up once the voltage reaches minus 50 millivolts and allows for the influx of sodium from the outside. So if you have a graded potential here that's reached this value, boom, this would open up, sodium start coming in. By coming in, so you had positive charges here, negative, right? These negative charges become a little bit less. And so the membrane potential will get depolarized, okay, further depolarized. So sodium is coming in, and this will go on. Notice that the potassium voltage gated channel is still closed at this point. This will go on until you reach a value of about 30 millivolts. Okay, so the membrane has dramatically depolarized up to 30 millivolt here. Now, when you reach this value, now you have the second component of the sodium voltage gated channel here, which is the inactivation gate. So the activation gate is still open, it can still carry sodium, but the inactivation gate here blocks the movement of the sodium at this point. So now the sodium has moved inside, at this point stopped moving inside, but the second voltage gated channel, which is the potassium voltage gated channel, now gets activated at 30 millivolt. So it opens up, and because now you have increased these, or changed basically the distribution of the charge here, and because of the concentration of potassium, which is much higher on the inside, it starts flowing outside. So at this point, now you have that this environment here has become more positive than this one, right? And that's the reason why you have a positive millivoltage there. But now potassium is going outside, and by doing that, now it's removing the positive charge from this side, bringing it to the outside. And this will quickly start causing repolarization of the membrane, right? So now the voltage will go down from 30 millivolt all the way to lower, ultimately you'll see in a second, lower than the resting potential. So the movement of potassium here is bringing down now the voltage to the resting value even lower than that. When this happens, so when this value reaches 50 millivolts, now you have that the activation gate also in the sodium voltage gate channel closes up. That's the value, like cutoff value for this gate. And also you have that now, since it's going down from 30 millivolts, the inactivation gate opens up. At this point, still you don't have movement of sodium here. You'll see this part here is important for what we call the refractory period. which is responsible for the unidirectional movement of actual potential. Now, potassium keeps moving in until the values here is reached, so that the channel here closes up. At this point, what you have a transient moment of actually hyperpolarization, but then the sodium potassium pump will start moving against sodium and potassium against their concentration gradient, re-establishing the membrane, resting membrane potential here. So all of this, again, summarizing, you had a graded potential that's reached the threshold value. You have here the activation of the sodium channel, okay, sodium voltage dependent channel here, opening of the activation gate there. Potassium moves inside, and this causes depolarization of the membrane. Certain point though, the inactivation gate closes up, stop the flow of sodium, but at this point you have the potassium voltage gated channel that opens up. It moves the opposite way than sodium, and therefore causes the repolarization of the membrane with a brief period of hyperpolarization here, and then the sodium potassium pump reestablishes here the resting potential. Now, how is this generated, and where is generated this? This can be generated, what we just talked about, can be generated by the summation of different graded potential which reach the threshold, or can be generated also at the level of sensory receptors. So certain neurons that basically do detect the stimuli in your body. So now what we're talking about here is the neurons that do basically detect, as we say, the stimuli here, and then they transfer them ultimately to the interneurons. These are afferent type of neurons. So now there are different type of sensory or afferent type of neurons. There are those that are made by dendrites, we'll see in the next picture, or those that are actually connected to specialized receptor cells. And now these they can detect different type of stimuli, such as light. For example, if you're talking about your eyes, heat, you have a lot of thermoreceptors in your hand, sound waves, and so on. Now, based on the type of stimulus that they can detect, sensory receptors here can be divided into 5 different groups. You have mechanoreceptors. For example, those receptors that we're talking about are the base that of sensing the stretching of the tendons, are referred to as mechanoreceptors. What they detect is mechanical changes in the environment. Then you have photoreceptors that can detect the energy of light. I'm sure you can think of some example in your retina right there. Chemoreceptors, which instead detect changes in some chemical parameters, such as concentration of protons, therefore acidity or pH, and or for example level of oxygen, so specific molecules. That's how, for example, your vasodilation is controlled through the action of chemoreceptors that do detect the level of oxygen and so on. Thermoreceptors, these, as the word says, they detect heat. You have lots of them in your hands. After this receptor that can sense, for example, high heat. And the last group is nociceptors. These receptors, they do detect pain. You have them both in internal organs or on your skin. Some of them do overlap actually with thermoreceptors as well, and or can detect not only physical mechanical type of damage, but also damage induced by different toxic chemicals. Now, depending on their structure, you can see 3 main types of sensory receptors. So 2 of them are basically consisting of directly the afferent neurons, or the dendrites of the afferent neurons are those parts that do detect the stimulus. Okay, and these can be of two different types. You may have that the dendrites are free, so you may have that afferent neurons with free dendrites or free nerve endings, which is where the stimulus is perceived, or you may have the second type where the dendrites here is encapsulated within a structure, for example in the tendon. That's the example I was giving you before. And so the dendrite now is detecting changes of the structure in which is encapsulated and translated into a stimulus. The third type is actually you may have specialized cells. Let's see some example here. So where you have a specialized cell, that detects the stimulus and then transfer it to the afferent neuron through synapses. For example, the release of a neurotransmitter, which then will stimulate the afferent neuron, which then will bring the signal to your central nervous system. So here you have some example of free or enclosed nerve endings type of receptors. So these are all neurons which have their dendrites, which can be either encapsulated, for example here in the Pacinian corpuscle here, to detect pressure. You can see this is the environment, by the way, under your skin, in your derma there. You can see how many types, for example, just pressure receptor you have in there. And that's the reason why we're so sensitive. You can interpret, you can close your eye and feel things so well. You have so many type of receptors there. Some of them do detect actually touch with free nerves, free dendrites here, which, for example, in this case, there are inside your follicle, and what they really detect, they indirectly detect touch by detecting the movement of hair caused by the touch. So if you have, say, this is your finger, the finger is not very hairy in this case, but your arm, for example, okay, you touch your arm very lightly, you feel the touch because you're actually moving the hair, and the movement is transferred to these nerve endings of this afferent neuron, this receptor ultimately, which will bring that stimulus to the central nervous system. Instead, when you have sensory, you may have sensory receptor cells dedicated to the perception of the stimuli. Think about your rods in your retina and so on. In this example here, these sensory receptor cells are those that are found, for example, in your cochlea. When it comes to hearing, okay, your hearing actually goes through the perception of sound, has to go through 3 different steps in your ear. So first, you have that the wave, the air wave caused by the sound waves caused by the sound are detected by your eardrum, your tympanic membrane here. So these sound waves would cause the vibration of this eardrum. These vibration now are transferred to the inner part of your ear, which is the cochlea here, by 3 bones, which are the middle ear bones here. So mechanically, they transfer these vibration, the sound wave here, to the cochlea. And here, basically, they transform it into movement of the liquid which is present inside the cochlea. And now the movement of this liquid here is transferred or translated into a sound by these sensory receptor cells. These are epithelial cells, modified epithelial cells, which are basically lining the all cochlea here. So imagine these completely covered by these cells that have cilia. And the cilia are there exactly to detect the movement that will move with the liquid, to detect the movement of the liquid. Now, you have cells everywhere here. And now what you have is that obviously depending on the type of sound wave you have, for example, if you have a bass, right? Very low. It's big wavelength, low frequency. What happens here is that this would be translated into a movement which probably would stop at a certain point inside here. So now you would have that this cell here in this region, but not the other one deeper inside the cochlea, would perceive that movement. So only these cells. Now the integration of all the information from this cell and this one here, so you have this activated but not this, will bring the information to your brain and will be perceived as a bass. Whereas if you have somebody screaming, and I have 2 kids, particularly a young one there, what happens when he screams, these sound waves are very high frequency, short wavelength. And what happens here is that now it translates into more movement of this liquid. And so it would activate not only these cells here, by the cells up to here. I'm sure my son can activate them even further. I'm pretty sure he broke my cochlea. Um, and the and so now having all of these cells activated at this point will be translated once the signal, all of this signal by all of these cells is brought to your brain, will be translated into a high pitch, so a big scream, and then this would activate your counter screaming. No, just kidding, but it would activate whatever response is necessary. So once they, so how does this, so no matter what is the receptor, how is this translated into a signal? Well, it's translated because the, whatever is the stimulus ultimately is causing, in these nerve endings, for example, or here, right here, in the postsynaptic membrane here, translates into graded potential. Graded potential that then can sum up. If there is only one graded potential every minute, for example, it wouldn't really translate into much. But if you start having a lot, let's say you compress this body, imagine this is a pressure sensing body. You compress a lot, now you start causing more and more and more graded potential here, which then ultimately could lead to the formation of an action potential and therefore the transmission of the signal. And so the amount ultimately of graded potential that you get there, it's what really causes the magnitude of so the it will be proportional to the magnitude of the stimulus. Will allow you to grade the level of the stimulus. You have a lot of pressure, just a little bit. Now, great. So that will lead to the generation of graded potential and potentially, an actual potential if that graded potential reaches the threshold at minus 50 millivolts. How is the signal propagated after an action potential has been generated? Well, first of all, the action potential will be generated at the axon hillock, okay, the region in the body of the neuron which is right at the bottom of the axon. That's where all the graded potential ultimately get integrated. We'll see it at the end when we'll talk at the end of this first part when we talk about summation. So that's where all that information gets collected, gets integrated, and eventually can be translated into an action potential. Action potential which then will move through the axon, going all the way to the end, all the way to where the axon will form one or more synapses. How is propagating from the axon hillock all the way to the synapses? Well, there are two different ways that can happen. There are, in some neurons, it would just propagate it in a continuous way. This takes place in those neurons that don't have the myelin sheath. You remember we're talking about Schwann cells and oligodendrocytes? Well, some neurons don't have them, all right? So they just have the axon, naked axon there. Usually these are short neurons with a fairly large diameter. They can work only at short distances. For example, an interneuron in your spinal cord could be this type of neuron. Whereas other neurons, they do go a long distance, they are narrower, their signal will fade very quickly and they need the presence of myelin around them. And so by doing that, the signal goes not in a continuous way, but we'll see what we mean by that, in a saltatory way. So let's talk about the continuous propagation, first type. Again, this takes place in neurons that have short axons and large axons usually. So how is it caused? Well, imagine this being the hillock area, right? So you have the generation, so the integration of all the signals coming from dendrites here has caused the generation of an action potential. Okay, now this action potential will have to go through this axon all the way to the different synapses here. How is this generated? Well, this is the original action potential. So what you have, as we say before, you have the activation of the sodium voltage gated channel here. This causes a depolarization of the membrane. Now, while this action potential is generated, now this depolarization gets sensed, similar to graded potential, also at a certain distance. So it gets sensed also by the membrane right downstream. So if this was here, a little bit further down in the axon, this gets sensed. So imagine this being more like a fading, grading here. So what happens that while this action potential is taking place, now you have the depolarization also of this section of the membrane right adjacent to where the first action potential is taking place. And this keeps going and going and going even further down. In this case here, this area is not affected yet. But what happens that now this action potential here, first, so it had the depolarization caused to the influx of sodium ions. Now you have the efflux, so the potassium start moving out. So you have that repolarization of this membrane. But at the same time here, now this depolarization here have reached the threshold value in the adjacent membrane. So the action potential here, which now is fading away in this region of the membrane, has caused another action potential here in the adjacent part of the membrane. And this, as before, is now depolarizing also the other side, the other adjacent part of the membrane. And so by doing that, basically you have an action potential which progressively moves towards this side of the action potential. And so this will keep going and going and going in a unidirectional way. Okay, so the action potential here causes enough depolarization in the adjacent membrane, and therefore another action potential which does the same thing on the further down section of the membrane, which does the same thing. By doing that, the signal goes through in a continuous way through this cell membrane. And all because obviously in all of these areas you have ultimately sodium voltage gated channels and potassium voltage gated channel all throughout this membrane. So they're present everywhere, so they get activated progressively one after the other. Now this goes, as I say, only in one direction. Why doesn't it go the opposite way? Well, the reason why it doesn't go backward, right? So this action potential transfer only to going towards the synapses ultimately in the axon is because of what we call the refractory period. So what happens is that while an action potential is happening, you have a moment here where the membrane, ultimately where this is happening, so imagine this membrane right here at the beginning, there is a moment, this moment right here, where is not sensitive to the polarization. So meaning that even if you have now an action potential happening here, obviously this action potential is still spreading. Imagine I'm going to use a pen now just to give you an idea. So even this action potential here is causing depolarization in both directions, right? But now what you have here is that in this part of the membrane here, which was where the original action potential was, the sodium channel is not sensitive to that anymore. It cannot be activated for a few milliseconds. So it's refractory in that little period. Why is that happening? Well, look at this. So what happens here? That's where we are at. So I'm trying to put all the information together. Hopefully I will not knock you out, but I want you to see it based on what we discussed before on how the action potential is generated. Again, the first part, remember this part here, is caused by the influx of sodium ions, right? Which takes place and then gets stopped at this level right here. Gets stopped because the inactivation gate here has closed the channel. Even though if this part is still open, the sodium ions cannot move anymore. So now what happens here is that you have a moment where this sodium channel cannot be activated anymore. So even though at this point right here, so that's where you are right now, right? This is the moment where the neighbor membrane, the adjacent membrane, will start having the next action potential, right? This is when, so if you're right here, right, and then you have that this will turn into an action potential, right? Shoot up, and this will be sensed back to this part of the membrane here, right? It's spiking up there. Gets sensed in this area here, then later on will convert into an action potential, but here it doesn't. So the action potential moves that way. Why? Because even though here now you might have reached the threshold value, you're still in a period where ultimately the sodium voltage gated channel are refractory, cannot open because of the inactivation gate still blocking them. Okay, and because of that, now then this area of the membrane here cannot cause another action potential anymore, but the other side could do that. Now, what we mentioned until now, and the refractory period is valid for both continuous and saltatory type of propagation. So we talked about the continuous propagation. Propagation that keeps going through the axon in a continuous way because there are the channels, sodium, potassium channel present everywhere throughout this membrane. Okay. In myelinated axons, so those long one and narrow neurons or axons that you have, instead this doesn't take place the same way. Instead, the signal takes place only a specific region called the nodes or envier, which are those places where you have a gap in between the myelin sheath. So these will be the node of Ranvier here, or nodes, just call them nodes, right here. So the signal here, the action potential ultimately happens only at these points, okay? But when it happens, because of the myelin sheath, the way in which so that's how it would happen here. So you have that this the way that the charge gets lost. So if you take any member, right, let's say, and you change, so you cause an action potential here. Imagine there is no myelin here. What you would have is that if there is nothing that keeps the ion here, holds them close to the membrane ultimately, so an unmyelinated type of neuron, what would happen is that if you look at the way the polarization spreads, will be like this. So you have this spike here, and it gets sensed, so obviously in the other side, both sides, but we would get sensed, it would dissipate ultimately quite quickly depending on the distance, right? Instead, if you have something that can now hold, so you have a myelin sheath around here, that basically can hold the ions here. The ions that come in and out here can be held close to the membrane. What you have is that actually this signal will dissipate much more slower, right? So what it means is that now, if this is your threshold value, you can only, if you have no myelin, you can only activate or transfer the action potential or reactivate only within a certain distance. But now if you have the myelin, you can do it at a much longer distance, right? If you still have sodium and potassium channels here, now here you have enough power to activate the sodium channels here, and then regenerate this. And the same thing could happen if you keep going here. So that's exactly what happens here in the saltatory conduction. You have that ultimately these channels are present only in the nodes, right? And so this is where the actual potential gets generated in the node or envier, but because of the myelin sheath, the depolarization gets sensed much farther, okay, to the next node. In the next node, you still have a depolarization which is higher than threshold value, and therefore gets translated into another depolarization, and so on to the next node. And so basically, you have, as you can see, the action potential is basically jumping, salta, that's how we say in Italian, is jumping from one side, from one node to another one. It's not continuous, but is jumping between nodes. And this actually makes the overall signal go much faster. So if you measure the speed at which this action potential is moving this action compared to a continuous or an action where you have a continuous conduction, you'll see it's way faster. And so this allows for the fast transferring of signal, for example, from your brain all the way to your feet. It's almost instantaneous. It would not happen if you had a continuous conduction taking place there. The other thing is that by having these, now you have that you can use much more narrow type of axons, which then can be compacted more and more together into nerves. So your nerves can be overall much slimmer compared to how they would be if all the axons were instead fairly large. So let's finish up this first part by talking about how is the signal ultimately, what happens once the signal reaches the end of the axon, so at the synapses, and how is this signal transferred to another cell, and how is integrated ultimately to regenerate another axon potential. So once the action potential reaches the end of the axons, right, it might be transferred to the effector cell, such as muscle fibers, for example, or to another neuron, like an interneuron. And this is done through synapses. Now, when we talk about synapses in general, you can identify two things. There is a presynaptic cell. That's the cell that is bringing the signal in. This will be the presynaptic cell. And then you have a postsynaptic cell. And a similar way you can talk about presynaptic membrane and postsynaptic membrane. And in between them, you would talk about the synaptic cleft. So how is the signal transferred from one neuron to another cell? Well, maybe another neuron, whatever. It can be transferred in two ways depending on the type of synapses. So there are two types of synapses. You have electrical synapses. As the word says, the electrical signal, ultimately, an action potential is nothing else than an electrical signal, is transferred directly to the other cell by basically transferring the ions themselves. And this is done through these gap junctions we talked about when we talked about them when we talked about the cell membrane, and we talked about, even when we were talking about tissues, how these gap junctions basically allow for the formation of opening in between two adjacent cells. So now the cytoplasm is in continuity between the presynaptic and the postsynaptic cells, and therefore even the ions can freely move through that. And by doing that, they allow for the propagation of the depolarization of the membrane, and therefore even the action potential can be transferred directly to the membrane of the next cell. The second type are the chemical synapses. Chemical synapses instead rely, as the word says, in a chemical to transfer, which is what we refer to as the neurotransmitter, to transfer the electric signal from the presynaptic cells to the postsynaptic cells. And this neurotransmitter binds to a receptor, which then would generate the signal. Now, so how does it work? Well, let's look at the pictures. It's easier to look at this picture to talk about chemical synapses here. So what you have is, this will be the presynaptic cell. Okay, so this is the cell that has the potential going through the axon. So we have reached the synapses here, and now the signal is ready to be transferred to the next cell. So what happens is that the actual potential here at the presynaptic cell will cause the opening of voltage-gated sensitive calcium channels. Calcium is more concentrated on the outside than in the inside, and therefore the opening of this channel will cause the influx of calcium from the outside to the inside. What does this do? It causes ultimately the activation of the release of vesicles which are already present inside. You can see them here in this electron microscopy picture. They are already present at the chemical synapses, and these are vesicles that are packed with the neurotransmitter. They stay there until signal comes, the calcium comes in, and then these vesicles here, they start moving towards the presynaptic membrane here, where they fuse, and when they fuse, they release the neurotransmitter. Now, the neurotransmitter then goes first into the synaptic cleft, and then it will bind to a specific neurotransmitter type of receptor. We'll see there are different types of receptors. And this is what will cause either the hyperpolarization or the depolarization of the following membrane. What happens once the signals stop, once there is no more action potential coming in, obviously the calcium channel will close, there will be no more calcium influx and therefore no more fusion of the synaptic vesicle here. So there will be no more fusion with the presynaptic membrane here, and therefore no more release of neurotransmitter. And the existing neurotransmitter left behind here would actually be removed by glial cells or be degraded ultimately there. And therefore, the stimulation of the postsynaptic cell will cease to exist. Now, when we talk about neurotransmitter, there are two types of neurotransmitter. There are direct neurotransmitters, which do bind directly with an ion channel, ultimately a ligand-gated ion channel. So they bind directly to and basically open the ion channel directly. Indirect ones, instead, they act through a receptor, which then activates a secondary message, which then would act on the ion channel. Now, no matter what type you're talking about there, they ultimately will work on some specific type of ion channels. Now, and depending on the one they work on, they will cause either depolarization or hyperpolarization. So now, if you have a neurotransmitter that ultimately activates a ligand-gated sodium channel, right, these ultimately will lead to the influx of sodium from the outside to the inside of the postsynaptic neuron. By doing that, if you remember, that's exactly what happens when you have the gradient potential and so on, you will cause depolarization of the membrane. If instead the neurotransmitter, and so that, sorry, this will be called an excitatory postsynaptic potential. The reason why it's called excitatory is because it brings the membrane potential closer to the threshold volume. Right. Instead, if the neurotransmitter leads to the activation of either a potassium ion channel or a chlorine ion channel, channel here, it will lead ultimately to hyperpolarization. Why? So if you open a potassium channel here, what you would have is that now the potassium will go from inside to the outside. This will lead to hyperpolarization. So you have even more negative charge here compared to the outside because you have more positive charge that moved out. The opposite happens with channels there, where you would have that basically the chloride here. So if you open the channel now, chloride is very highly concentrated on this side, we'll move towards the outside. From the outside we'll move towards the inside, and therefore we then reach the inside environment with negative charge, and this again would cause hyperpolarization. Now, this is referred to as an inhibitory postsynaptic potential because actually it takes the potential farther from the threshold value, which is necessary to activate the action potential, which ultimately leads to the activation of the recipient cells. So now, how does it translate all of this? Well, we talked about different action potential reaching a synapses, which then will stimulate a postsynaptic neuron. Now, you have to understand one thing is that the neuron, the postsynaptic neuron, can be receiving thousands of synapses. And that's exactly the beauty of the nervous system, is that at this level, these neurons, imagine this being an interneuron or a Purkinje neuron in your cerebellum, you have thousands of different synapses connected to the same neuron, right? And all of them bring in some sort of polarization of depolarization. So bring in an excitatory or an inhibitory postsynaptic potential. And all of this information ultimately gets integrated by the recipient neuron, so the postsynaptic neuron here, and might or might not generate a specific action by this neuron with a certain frequency and so on. And so basically all this information at this level get integrated. Like really it's a super high level of integration that we're talking about here. How does it get integrated? Well, first of all, it gets integrated in this region. So you have all of these synapses that can cause hyperpolarization or depolarization, right? Which would transfer to the cell body ultimately, and ultimately will reach the axon hillock here. And here they get put together. Depending on the effect that you have on the membrane potential here, you might have or not have the generation of an action potential. And so what we're talking about here is the process of summation, again, taking place here at the axon hillock. Now, there are two types of summation. There's the temporal and spatial summation. Temporal summation, you talk about temporal summation where you're talking about how the different graded potential generated by a single synapses are added together. So imagine you have a neuron with a single receiving a single signal, so through one synapses. Now imagine this signal can be very slow or very low frequency, so you have 1 per second. So what happens there, you would have something like this. Every time the synapse gets stimulated, you get a graded potential, not enough to reach the threshold value. This slows down. Then the other second later, get another one. But these don't really add together, so there is no summation. But now, if you increase the frequency, you start having, instead of every second, every 1/10 of a second. So you start having tick, 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 something like that. Now, there is not enough time here in between for the membrane potential to go back to the resting value. And so these will start actually building up. And no, you can have what is called the temporal summation, which at a certain point will allow for the membrane potential to reach the membrane potential, to reach the threshold potential here, and therefore you would have that this summation, this temporal summation, will lead to the formation of a action potential. This is different from spatial summation, where you have instead that two different synapses, or the graded potential generated by two different synapses, get added together, right? So for example, in this case, this one and this one right here, if they're both active at the same time, it's possible when they reach the depolarization reaches this point here, they will be added together, reaching the threshold potential, and therefore causing the formation of an action potential, which then would spread through this axon. Sometimes what happens instead, though, you might have, instead of having summation, you get what is called a cancellation. And this happens when you have an excitatory type of synapses here, so which works together with the uninhibitory synapses here. So you have that these will be causing depolarization, these will be causing hyperpolarization. And so what you have there is that if both are active at the same time, they may actually cancel each other, like in this example right here. So the potential of the membrane doesn't change at all, because one of them brings depolarization, the other one brings hyperpolarization. When they act together, they will cancel each other. And again, it's still part of integration of the signal, right? All of that. Okay, we'll stop here. In the next part, we'll finish up much more quickly, talking about the evolution of the nervous system and the structure of the human nervous system.